In this video, I'm going to talk about the curvature and components of acceleration. In this video, I'm going to consider in greater detail the acceleration vector introduced in the previous video that I put a link to it. But before doing this, we need to examine a scalar quantity called the curvature of a curve. In this video, I'm going to also talk about a unit tangent vector. I'll define it, then I'll define the curvature of a curve, and then I'll go through the tangential and normal components of acceleration. Then I will give different formulas for acceleration and also the curvature, and at the end I will define the radius of curvature. I will also put a link to my website for these review notes on the same topic. So now let's define the unit tangent vector. Let C be a smooth curve in either 2 or 3 space traced out by a vector function r. We know that r prime t is a tangent vector to the curve. From the previous lecture video, we know that if rt is the position vector, then r prime t will be the velocity vector, where velocity at any point is tangent to the curve. And we also know that to define a unit vector, we need to divide that vector to its magnitude. So since in here we want to define a unit tangent vector, and also we know that the velocity vector is tangent to the curve, so the unit tangent vector to the curve will be defined as this vector here, where this is the velocity and this is the speed or the magnitude of the velocity. So if we draw the vector t on a curve, we will have this. So as you know, the vector t always has a magnitude of 1, but its direction will change as our point changes its position on this curve. So the vector t is called a unit tangent. And if c is parameterized by arc length s, then a unit tangent to the curve is also given by this. And we also know that the quantity of r prime t is related to arc length by this equation, where the right hand side is the speed or the magnitude of the velocity vector, and the right hand side is also the same. But let's assume that our point is initially here, and then after some time it moves to this point. So then the displacement here will be equal to ds, the length of this arc, and the time that it takes to move from this point here to this point here will be dt. Then we know from the definition of the velocity that the velocity is equal to displacement in space divided by the time unit that it takes for this displacement. And again, from the previous video, we know that the velocity vector is equal to this fraction, which will be equal to using the chain rule. Then from here, we can find dr over ds, where dr over dt is the derivative of r with respect to t, and ds over dt is equal to the magnitude of the velocity vector, and this is equal to the unit tangent vector. So on this curve here, as s increases, t moves along c, changing direction but not length, and we know that the length of this vector t is always equal to 1. So now from point p1 to point p2, the direction of vector t changes a little bit, but from point 2 to point 3, where c obviously bends more sharply, the change in the direction of the tangent t is more pronounced. So we can use the rate at which the unit vector t changes direction with respect to arc length as an indicator of the curvature of a smooth curve. So the curvature of c at a point will be defined as the magnitude of this fraction. Now we can use the chain rule and write this fraction, which will be equal to this one. So then the curvature can be expressed in terms of a general parameter t. Now let's define the tangential and normal components of acceleration. Let's say that P is a point on the curve C, and we want to find the components of the acceleration there. So let's say that this is the vector of acceleration, then this will be the tangential component, and this will be the normal component. And these two vectors our unit normal vector and unit tangent vector. So if the particle is described by the vector function rt, then the velocity of the particle on curve C will be equal to the first derivation of r, and its speed is equal to ds over dt, which is equal to the magnitude of the velocity vector. And since the velocity vector is tangent to this curve, then we can say that the velocity vector is equal to the magnitude of the velocity times the unit vector to its direction. We know that the acceleration is defined as the second derivative of r, or the first derivative of the velocity vector. So differentiating this equation with respect to t gives us the acceleration. And we know that this vector is perpendicular to this vector. So now we can form a unit normal vector by finding the unit vector in the direction of this vector. So this will be a unit normal vector, and we call it the principal normal. Using the definition of the curvature, we can find the vector dt over dt. So now we can go back to this equation and write the acceleration vector. So this term is the normal component, and this term is the tangent component. So note that here the tangential component of the acceleration results from a change in the magnitude of the velocity vector, whereas in here, the normal component of the acceleration results from a change in the direction of the velocity vector. So now let's define the binomial. Here I took this figure from the textbook, and a third unit vector is defined by the multiplication of the tangent vector and the normal vector. So the cross product of the unit tangent vector and the unit normal vector using the right-hand rule results in this unit vector b, and this is called the binormal. The plane of t and n is called the osculating plane, and we will call the plane of n and b the normal plane, and the plane of t and b is the rectifying plane. So these three orthogonal unit vectors can be thought of as a movable right-handed coordinate system. And this movable coordinate system is referred to as the t and b frame. And we will have these equations. Now we can find formulas for the tangent and normal component of acceleration, and also the curvature involving r prime, and r double prime. So I will write all the equations and then I will prove them. For the tangential component of the acceleration, we can form this dot product, which is equal to, so this is the velocity vector and this is the acceleration vector. And the dot product will give us this equation. So then we can write that the tangential component of the acceleration is equal to VAT divided by V, which is equal to this fraction. We just saw here that V dot A is equal to VAT, and also we know that this V is the magnitude of the velocity vector. So the velocity vector is the first derivative of r, the acceleration vector is the second derivative of r, and again, the velocity vector is the first derivative of r. Then for the normal component of the acceleration, we will write the cross product of the velocity and acceleration. So we will have this equation here, which will be equal to, and we know that this is equal to 0, and this is equal to vector b. So this will be equal to a and vb. And we know that the magnitude of vector b is equal to 1 because it's a unit vector. So the magnitude of this cross product will be equal to the magnitude of this vector here, which will be equal to an divided by an times v. And if we divide it by the magnitude of the velocity, we can find the normal component of the acceleration, which we have it here. So this is vector v, this is the vector a, and again, this is vector v. And also we know that the curvature is equal to the normal component of the acceleration divided by the velocity squared. So an divided by the velocity squared will be this equation here, Now let's define the radius of curvature. Let's say that we have a curve and we want to find the radius of curvature at point P. As we know, this line is tangent to the curve at point P. The radius of curvature at the point P on a curve C is the radius of a circle that fits the curve there better than any other circle. So let's say that this is the best circle that can fit on curve C at point P. Then the center of this circle will be the center of curvature, and its radius will be the radius of curvature. And we show it by rho. The radius of curvature is the reciprocal of the curvature. I hope that you enjoyed this video, and if you have any question, just write in the comments.